APIs have become a strategic necessity for many businesses. They can be the cornerstone for driving agility and innovation in an organization. However, many organizations are still struggling to balance the opportunity with the risk of unauthorized access of the valuable information that the APIs expose. Now, according to Gartner, by 2022, API abuses will be the most frequent attack vector for enterprise web application data breaches. So it's easy to see why many IT decision makers today are so concerned about API security. An API security approach is based on several layers, and we provide an in-depth look at each of these in MuleSoft's API Security Best Practices white paper. Hi, my name is Mike Moore. I'm a Technical Architect Director with MuleSoft's Customer Success Strategy and Architecture team. Today, we're going to focus on one of the primary areas for securing APIs, which is identity. Now, a secure API is one that only exposes its data to users, apps, and servers who are authorized to consume it. We'll look at out-of-the-box ways that API Manager can be used to validate the incoming requests and provide verified identities to the calling apps and the users so that the API only returns the appropriate data to the appropriate consumer. So let's get started.
Identity is core to the world of security. You must be able to recognize the apps that consume your API, the users of the app consuming your API, and the servers that your API calls out to. Likewise, your API should be able to identify itself to both apps and servers. As it relates to using API Manager to secure APIs, we're going to focus on the first two situations. Identifying the application consuming the API tells us if the client application is allowed to call the API. We may also validate if the client application is allowed to make the type of request that was submitted to the API. Our use case may also require understanding the user interacting with the application that consumes the API. And similarly to the application, we may need to allow the API implementation to make a determination on what the user can see and what they're able to do. This diagram illustrates the common areas for an app to API authentication. We need to validate that the mobile app is allowed to call the e-commerce API at the edge, and also prevent access from unauthorized apps being able to call the API. It's common in API-led architectures for an experience or process API, like the e-commerce API, to call other APIs like orders. We do not want to only secure the e-com API. It's best practice to secure each interface, providing only the right level of access for each consumer. In this model, the API implementation of e-com is also a client application of the orders API, and the orders API implements its own security and governance policies. We can also add in user context to this model. Though we have an end user in this diagram, the security between the mobile app and the e-com API and the e-com implementation and orders API still exist. We can use certain frameworks and policies to also include information about the user themselves for data filtering and ensuring the user approves of the actions that the mobile app is taking on their behalf. So along with the user, app, and API or server, providing identity and securing access requires two additional functional components: an identity store and an identity provider. The store is a repository for clients, users, and their credentials, and other attributes like certificates, roles, and entitlements. This could be something as simple as a database or an object store. Typically, organizations will use something like LDAP, with Active Directory being a popular LDAP implementation. Identity providers provide an interface over an identity store. They may have workflow, audit tracking, and can federate many different identity stores, such as internal users versus external users. An API could be its own provider, for example, using basic authentication policies, but it is best practice to centralize and delegate this function. When you register a client application in the Anypoint platform and apply client ID and secret policies, the Anypoint platform acts as an identity provider and store. Let's recap the various functional components that are involved. It's important to remember that some functions could be fulfilled by different actors. The identity provider provides an interface over the identity store. It validates that an application consuming the API or user should be allowed to access that API. The platform can do this for application authentication. A federated identity provider like Okta or Ping Federate provide an industry standard mechanism via OAuth and OpenID Connect. You could also leverage a custom or legacy authentication and authorization framework that your enterprise may already have. Or finally, the API implementation could implement its own security. The identity store could be a database, or more commonly, a LDAP to hold users, attributes, roles, and other credentials. Consumers of an API like the mobile app here are referred to as a client application, or application. And an application has a contract or approval to access an API in the context of API Manager. A resource is the API or proxy that the client application needs to connect to. A target could be another API or downstream system that the API is interacting with to fulfill its implementation. And it's important to remember that an API implementation will likely be a client application as well, since it needs to authenticate and be authorized to access a database or other API in the application network. There are two main ways to authenticate users or apps to consume an API. Credential-based relates to a consumer presenting secrets directly to the API or proxy. Common mechanisms for this method are username and password, in which an API implementation is acting as an identity provider. Client ID and secret, which uses generated IDs and secrets that are specified in the request and validated by the endpoint platform or third-party identity provider. And certificates, which are validated by the API implementation against a trust store in the client application and the API implementation. In these models, the credentials are shared with every request to the API. Token-based authentication leverages a separate authorization server or identity provider, and the client app or user interacts directly with this initially. JWT tokens or opaque tokens are issued with a short time to live and can be revoked without changing the client credentials. The credentials are exchanged directly with the identity provider and not with the API implementation. The API receives a token and can use API manager policies to validate the incoming request. And while the tokens do not contain credentials, they can store many different attributes about the request, including ways to validate that the token is genuine, the user context, client app identifier, roles, scopes, and other attributes that can be used by the API implementation to determine what data to return and which actions to permit. Let's quickly review the mechanisms and some of the pros and cons to consider. Let's first take a look at the credential methods. The first is username and password. And while this is the easiest to implement and supports user authentication and app authentication, it has several disadvantages, specifically that passwords are predictable and they're hard to manage when they need to be rotated. We also commonly find that the same username and password ends up being shared across multiple applications, which can be a security risk and also mean that when you do need to rotate these, you have to make many different changes in your environment. With username and password, you also cannot include attributes about the app or the user itself. It also requires that the client app or API act as an identity provider or identity store because it's going to receive the username and password credentials. Client ID and secret is most commonly used for app-to-app authentication or app-to-API authentication because it's very easy to implement, being that it is completely managed by the endpoint platform. It can only be used for app authentication, but it is a bit better than username and password because there's a higher entropy than username and password, given that the client IDs and secrets are randomly generated. There's a unique credential for each client application, and it can be reset or disabled temporarily. It's important to remember that this can only be used for identifying a client application, so we cannot include any attributes about the application or the user itself. Client ID and secrets may be issued by the endpoint platform or an external identity provider like Okta or Ping. And it's important to remember that the client app has to be able to protect the client secret, so it may not be the best fit if you're building a single page application or a JavaScript client where you cannot protect secrets. The last mechanism is a mutual TLS certificate exchange. This is really useful for app authentication, and it allows the server and client to securely validate each other. It's important to remember this is only suitable for server-to-server interactions where you don't have a user context that's necessary, and it requires an exchange of keys between the server and client beforehand. It is more difficult to rotate the credentials because the certificates need to be added to a key store or trust store and potentially bundled and deployed with the application. Also consider that the server controls whether client authentication occurs. The client cannot force authentication or identification of itself. And it does require that you implement HTTPS. Looking at token-based authentication mechanisms, the first we're going to look at is JWT, and it can be used for user and app authentication. JWT is really a token format, so this refers to any custom user store and authentication or authorization implementation that you want to use. JWT tokens can store attributes, roles, and other data about the client app or user. If you're going to use this method, you have to create a process or API to be able to issue the tokens, and you also need a way to incorporate the client ID from the platform to be able to use other API manager policies like quality of service. The token can be validated locally by API manager using the JWT validation policy. Finally, we'll look at OAuth and OIDC, which are industry standard formats for user authentication and app authentication. It delegates auth to centralized systems and processes, usually a third-party provider like Okta or Ping Federate. It's suitable for many different authentication authorization requirements, including client apps that may not be able to protect secrets, user, and system-to-system communication. It issues short-lived revocable tokens and can store attributes, roles, and other data about the client application or the user. And client identification is natively supported using OAuth. It does require a separate identity provider, and the initial setup is more complex. It's important to also keep in mind that you're restricted to the OIDC specification and the provider implementation of your choosing. Depending on how you are issuing tokens, they could be validated locally or against the identity provider's introspection endpoint. OAuth supports scopes to further refine user and application API access. And as mentioned earlier, OAuth flows support insecure clients, such as using auth code with proof key for code exchange. So beyond authentication, APIs also have to manage authorization of the incoming request. Depending on the use case, a client app may be authorized to call an API, call only a subset of the resources or methods within an API, or perform actions on behalf of an authenticated user. Token-based access control permits the last two use cases by providing additional attributes, user contexts, scopes, and claims that allow API manager policy or an API implementation greater control over the actions and data it presents. OpenID Connect and OAuth are industry standard formats and protocols for implementing token-based access control. Some of the common examples would be mapping resources and methods within an API definition to those a user permits an application to perform, or filtering and masking data depending on that user's level of access. So let's walk through how all of this might be set up in the platform. For simplicity, we're not going to focus on which policy or authentication mechanisms are being used, as the pattern between the applications and APIs or servers remains the same. However, we will assume that we're using token-based mechanisms for the user interaction. Orders API is secured by API manager policies that govern access. A client application is created in the platform for the eCom API implementation. Depending on the implementation, the Anypoint platform or a third party like Okta would act as the identity provider and issue a client ID for the eCom API implementation client application. Request for access to the Orders API is submitted and then approved. Approving access creates a contract in the Anypoint platform between the eCom client app and the Orders API. The eCom client app is now authorized to call the Orders API. The same process occurs to secure the eCom API. Create a client for the mobile app and request access for the mobile app to be able to call the eCom API. Now that we've got the APIs authorized and the mobile client app authorized, let's look at how a user interaction would work. The user is going to start interacting with the mobile app, which is going to need to authenticate the user. The app will direct the user towards the identity provider to authenticate. Typically, the user will interact directly with the interface the identity provider exposes so that the app does not have any secure credentials or secrets from the user. Once the user is authenticated, the identity provider will issue a token back towards the application. The token contains information about the user itself, as well as the client application and the actions that it expects to perform on behalf of the user. The application can then use that token to call the eCom API on behalf of the user. The mobile app then sends its token when calling the e-commerce API. API Manager policy validates the eCom API can be called by the mobile app by checking the token and the information included inside of it. The eCom API as a client application then calls the Order API, including its own credentials or token. API Manager policy validates the Orders API can be called by the eCom client application. Briefly, let's touch on another way that you could secure your APIs. One way is custom code, and under the covers, Mule is Java code with configuration that's stored in XML, and it's capable of extending other pieces of Java code to secure applications. Java has frameworks such as Spring Security Authentication Framework, which could implement OAuth 2.0 and OpenID Connect capabilities. It's important to remember that custom code is, by nature, brittle and requires ongoing maintenance. The security implementation becomes embedded inside of the applications, which tightly couples the applications to the security policies. So any change in the policy requires changes to the API implementation code, testing, and redeployment. Ultimately, the security implementation becomes a development concern for each project and requires specialized understanding of security standards and implementation. Unfortunately, many teams implement security controls inconsistently, which adds confusion and increased risk of mistakes. It is recommended to externalize security, governance, and quality of service into reusable, configurable patterns that can be applied consistently across projects as an operational function without code modifications. API Manager and API policies can provide this level of standardization and flexibility. Out of the box, API Manager comes with many policies. Let's take a look at the ones that are related to security and access along the left. These are the policies that are utilized to better secure your applications, as well as the systems that they are accessing. HTTP Basic Authentication authenticates using username and passwords, which are configured in a security manager associated with the policy. An LDAP authentication policy authenticates users using configuration details for an open LDAP or Active Directory LDAP, which is already configured and running inside of your enterprise. IP permit and deny policies deny or permit calls only from IP addresses present in the list. And this can be useful if you're exposing APIs to a known subset of internal or external IP addresses. JSON Web Token Validation Policy can parse an incoming JWT token, validating the client ID, issuer, and other custom attributes and claims against the API that is being accessed. The Mule OAuth 2.0 Access Token Enforcement Policy works in conjunction with a custom Mule app acting as an OAuth provider to validate access tokens. It's important to note that this policy is only used with a custom OAuth implementation built using the Mule application template. Other OAuth providers would use the OpenID Connect Access Token Enforcement Policy. The OIDC Access Token Enforcement Policy validates incoming tokens that were issued by Ping Federate, Okta, or OpenAM OAuth provider, or any other OAuth provider that supports the OpenID Connect specification. Lastly is client ID enforcement, and while primarily this is a compliance policy, it can identify an incoming request to known clients and restrict API consumption for only approved client applications. As we look at this example, you can see that there are many applicable policies for the various layers of API-led connectivity. The important thing to note here is that this is no longer a responsibility of each individual development team that are building each node in the application network. Access control, quality of service, logging, and transformation can be applied consistently to the appropriate APIs that require them. And this applies for custom policies as well. If there is a need for a custom policy, it can be defined once and applied consistently across the APIs that need them, rather than baking that logic into every individual application or project. And this is what we would refer to as a layered security approach. We layer security and governance across APIs and integrations in a uniform manner, which removes the responsibility of security and governance from developer teams and keeps the API implementation focused on executing business logic.
Thanks for watching. I hope this provided valuable insight into how identity and API Manager play into a layered security approach for APIs. Please be sure to download the MuleSoft's API Security Best Practices white paper and look for future Friends of Max videos.